Two particles instantly mirror each other across a billion light-years. This is quantum entanglement, a spooky connection that defies everything we know about space and time. It is like an unbreakable bond between cosmic twins, where a change to one immediately affects the other, no matter the distance. By the end of this journey, you will see the universe in a completely new light. We are about to explore 30 incredible theories that place this bizarre phenomenon on the grandest stage of all, from the idea that entanglement weaves the fabric of spacetime itself to the possibility it could power a galactic internet. What cosmic secret do you think this strange connection is hiding? This instantaneous mirroring suggests a hidden network operating beneath reality. The first theory proposes that quantum entanglement is a cosmic communication web, a fundamental architecture linking the universe. Imagine every entangled particle as a single node in a vast, invisible internet, capable of transmitting information across any distance without delay. This concept directly challenges a cornerstone of modern physics, Einstein's theory of relativity, which states that nothing can travel faster than light. Yet here, a change in one particle is reflected in its partner instantly, seemingly breaking the universal speed limit. The implications are staggering. An advanced civilization could use such a network for flawless, instantaneous communication between stars or even between galaxies. It would be the ultimate tool for coordination and knowledge sharing on a scale we can barely comprehend. However, a major obstacle stands in the way, known as the no communication theorem. This principle states that while the particles are connected, we cannot actively control the random outcomes of their states to send a deliberate message like we would with radio waves. It is like having a telephone line where both ends ring at random, unpredictable times. You know the line is active, but you cannot choose when it rings or what is said. Despite this, the pursuit is far from over. Scientists are actively developing concepts like quantum repeaters, devices that could extend and manage entanglement over vast distances, potentially one day forging a controllable quantum channel. The dream of a universal internet built on the spooky links of the quantum world continues to drive exploration into this profound mystery. But if entanglement is a cosmic internet, what if it is also the very material the cosmos is woven from? This second theory ventures into the most profound depths of physics, suggesting that quantum entanglement might be the invisible thread stitching the fabric of spacetime itself into existence. This radical idea is crystallized in a concept known as the AR equals EPR conjecture. It proposes a shocking equivalence between two ideas that were once thought to be completely separate. On one side is EPR, named for Einstein, Podolsky, and Rosen, which describes the spooky connection of entangled particles. On the other is ER, an Einstein-Rosen bridge, which is the formal name for a wormhole, a hypothetical tunnel through spacetime connecting two distant points. The conjecture boldly states that these are not just similar ideas, they are two different descriptions of the same fundamental phenomenon. Every pair of entangled particles, according to this view, is connected by a microscopic wormhole. Think of the universe as an immense, intricate tapestry. The stars and galaxies we see are the brilliant patterns on its surface. Quantum entanglement, then, are the countless invisible threads on the backside of that tapestry, pulling and linking different points together to create the smooth, continuous fabric we perceive from the front. Without these threads, the tapestry would fall apart into disconnected, meaningless frayed cloth. In the same way, without the underlying network of entanglement, the very geometry of space and time might simply unravel. This provides a breathtakingly elegant potential solution to the greatest problem in modern physics, the conflict between Einstein's general relativity, which governs the large-scale universe, and quantum mechanics, which rules the tiny subatomic world. Gravity, described by relativity as the warping of spacetime, has stubbornly refused to fit into the quantum framework. But if spacetime itself is a tapestry woven from quantum entanglement, then gravity may not be a fundamental force at all. It could simply be a side effect, an emergent property of this deeper, more fundamental quantum connectivity. The force that holds our feet to the ground and guides the planets in their orbits might just be the collective pull of a universe stitched together by countless spooky threads. This idea that spacetime is woven from entanglement leads to an even more astonishing possibility. What if our entire universe, with all its depth and dimension, is merely a projection? This is the third theory, known as the holographic principle. It proposes that our seemingly solid three-dimensional reality is actually a hologram, a vast and incredibly detailed illusion projected from a flat, two-dimensional surface at the cosmic edge. All the information needed to describe every star, every planet, and every one of us is encoded on this distant boundary, like the data on a Blu-ray disc. And the mechanism that performs this miraculous projection, that translates the two-dimensional code into our three-dimensional experience, is thought to be quantum entanglement. The countless spooky connections between particles are the very threads that stitch the information from the flat boundary into the rich, textured reality we move through. Think of it like a cosmic movie theater. The two-dimensional surface is the film reel containing every single detail of the story. Quantum entanglement is the projector's brilliant light, shining through that reel and bringing the three-dimensional movie to life on the screen of our universe. Without that light, the film is just a flat, transparent strip, meaningless and inert. Without the dense web of entanglement, the three-dimensional world would simply not exist. If this is true, then every entangled pair is not just a strange link, it is a fundamental part of the universe's ultimate data storage system. Your memories, the feeling of sunlight on your skin, the vast emptiness between galaxies, all of it is emergent information. Reality, as we know it, is not the primary thing, it is a consequence, a grand illusion born from entangled relationships on a distant, two-dimensional surface. This forces us to ask a profound question. If our world is a hologram, what or who is holding the projector? Yet the holographic universe is not the only cosmic structure potentially built by entanglement. This profound connection might also have been the very engine that set our entire reality in motion. The fourth theory suggests that quantum entanglement was the driving force behind cosmic inflation, that unimaginably rapid expansion of the universe in the first fraction of a second after the Big Bang. To understand this, we must look at the vacuum of space, which is not truly empty. According to quantum field theory, it is a seething, bubbling sea of virtual particles constantly flickering in and out of existence. These transient particles can become entangled, and this roiling quantum foam possesses a bizarre property, a kind of energy that generates repulsive gravity. Think of it like this: gravity, as we experience it, is always attractive, pulling things together. But this repulsive gravity from the quantum vacuum would do the opposite. It would push space itself apart with incredible violence. Now imagine the universe in its first fleeting moment, a tiny, incredibly hot and dense speck where every part of this speck was entangled with every other part. This universal entanglement provided the fuel. When triggered, that repulsive gravity inherent to the vacuum exploded outward, inflating the universe from smaller than a proton to a vast cosmic landscape in less than a blink of an eye. This wasn't an explosion in space, it was an explosion of space itself, driven by the spooky connections woven into its very fabric, and we may have direct evidence for this incredible event. The afterglow of the Big Bang, known as the cosmic microwave background radiation, blankets the entire sky. This faint whisper of heat is not perfectly smooth. It contains tiny variations, a specific pattern of hot and cold spots. Scientists propose that these patterns are not random. They are the fossilized imprint, the ancient snapshot, of those primordial quantum entanglements from the universe's first moment. The microscopic quantum jitters of the inflationary field were stretched to cosmic proportions by the inflation they powered, permanently etching a record of the universe's quantum origins onto the sky. This means the large-scale structure of the cosmos, the vast web of galaxies and voids we see today, might trace its lineage directly back to the spooky connections that once filled all of space. That same entanglement which may have built the cosmos also threatens to unravel one of its most fundamental laws. This brings us to the fifth theory, a confrontation with the infamous black hole information paradox. At its heart is a simple but devastating question. What happens to the information about an object when it falls into a black hole? Information, in the quantum sense, is the complete description of every particle, its properties, its relationships, everything that makes that object unique. According to the bedrock principle of quantum mechanics, this information can never be truly destroyed. It can change form, but it must be conserved. Yet, Stephen Hawking presented a powerful argument that black holes shatter this rule. He showed that black holes are not completely black. They slowly evaporate over astronomical timescales by emitting what we now call Hawking radiation. This radiation, however, is purely thermal. It is random noise like the heat shimmering off a pavement, and it carries no information whatsoever about what fell in. So, if the black hole eventually evaporates completely, leaving behind only this featureless radiation, where did the information go? It seems to have vanished from the universe, a direct violation of quantum law. This set up a crisis in physics, a choice between the integrity of quantum mechanics and our understanding of gravity. The solution may, once again, lie in quantum entanglement. The concept of black hole complementarity offers a way out. It proposes a truly mind-bending idea. From the perspective of an outside observer, the information of an object falling into a black hole never actually crosses the event horizon. Instead, it is smeared and encoded onto the surface of the horizon itself, the point of no return, in an incredibly complex and scrambled pattern. This encoding is made possible by a dense web of quantum entanglement linking the interior of the black hole to its surface. Now, here is where Hawking radiation enters the picture in a new light. The radiation is not just random energy boiling off from empty space. The process that creates a pair of Hawking radiation particles involves one falling in and the other escaping. Their quantum states are deeply entangled. As the black hole evaporates, these entanglements transfer the information that was stored on the horizon out into the universe, imprinted onto the escaping radiation. It is not a clean, readable message. The information is scrambled like a priceless document put through a shredder, but the theory suggests that every single piece is still there. In principle, with a perfect understanding of the laws of physics, one could collect all the Hawking radiation from the black hole's entire life and unscramble it, recovering the complete information about everything that ever fell in. The information was never lost. It was just on an incredible journey, first frozen on the event horizon and then slowly radiated back out, one entangled particle at a time, preserving the universe's most sacred law. Our universe might not just be governed by computation, it might literally be one. The sixth theory posits that the cosmos is a colossal quantum computer, and every event within it, from the birth of a star to the fall of a leaf, is part of an unimaginably vast calculation. The fundamental units of this computer are not silicon chips but the fabric of reality itself, with entangled particles acting as its quantum bits or qubits. These qubits are the engine of this cosmic machine, capable of being in multiple states at once thanks to superposition. And it is quantum entanglement that links them together, creating a network that allows the universe to perform an astronomical number of calculations simultaneously. This is parallel processing on the ultimate scale, a cosmic distributed system of unimaginable power and efficiency. The evolution of the entire cosmos, from the explosive flash of the Big Bang to the slow, graceful dance of galaxy formation, can be seen not as a series of random accidents, but as the output of this ongoing deterministic computation. What we call the laws of physics, the consistent rules that dictate how matter and energy interact, may simply be the algorithms this cosmic computer is running. Gravity, electromagnetism, the nuclear forces, they are not fundamental truths etched into the universe, but the operational code, the software that the hardware of spacetime is executing. Think of a simple computer game. The world you see on the screen with its characters and landscapes is not real. It is an emergent property, a consequence of the underlying code being processed by the machine's hardware. In the same way, our three-dimensional reality, with its stars and planets, could be the magnificent visual output of a computation happening on a more fundamental, perhaps two-dimensional level. This raises a staggering possibility. If the universe is a computer, what is it calculating? Is it simply computing its own existence, its own evolution? Or is it running a simulation for some purpose beyond our comprehension? The processing continues with every entangled connection, writing the story of reality one quantum operation at a time. The information paradox reveals how entanglement might preserve data, but what if these spooky links could also become our highways to the stars? The seventh theory takes the idea of entanglement as a microscopic wormhole and asks if we could ever pry it open, transforming it from a fragile thread into a stable, traversable bridge. This builds directly on the ER equals EPR conjecture, which posits that every entangled pair is connected by a tiny wormhole. The monumental challenge is that these natural wormholes are unimaginably small and unstable, snapping shut in an instant. To create a passage a person or a ship could actually use, you would need to find a way to hold the throat of the wormhole open against the crushing force of gravity trying to seal it. Theoretically, this requires a substance with a truly bizarre property, exotic matter. Unlike the normal matter that makes up our world, exotic matter would possess negative energy density. Think of it not as a physical bar to hold a door open, but as a kind of cosmic repulsion, an anti-gravitational force that pushes the walls of the wormhole apart, preventing its collapse. The energy requirements for creating and stabilizing even a small, traversable wormhole are astronomical, far beyond anything our civilization can currently conceive. Yet the potential payoff is the stuff of science fiction dreams. A successfully opened wormhole bridge linking two entangled points in space would create an instantaneous shortcut across the universe. A journey that would take a conventional ship tens of thousands of years could become a single step through a stable gateway. This would not just revolutionize interstellar travel, it would fundamentally alter our place in the cosmos, turning separate star systems into neighboring towns. The implications grow even more strange when we consider time. The same laws of general relativity that allow for wormholes also suggest that certain configurations could become time machines, connecting not just different places but different moments. While this remains one of the most speculative ideas in theoretical physics, it is pursued with serious intent by renowned scientists. The dream of using the universe's own quantum stitching as a blueprint for our greatest voyages continues to inspire the very edges of our understanding. But even as we contemplate building bridges across space, a more fundamental question emerges. Why does time itself seem to have a one-way street? The eighth theory delves into the deep and puzzling connection between quantum entanglement and the arrow of time. We all experience time flowing in one direction, from the past we remember to the future we cannot see. The laws of physics, however, are mostly time-symmetric, meaning they work just as well running forward as backward. So why does our universe have such a strong preference for moving forward? The answer may lie in a concept called entropy, which is a measure of disorder. The second law of thermodynamics states that the total entropy of the universe always increases, and this relentless slide into greater disorder is what gives us a direction for time. A shattered glass does not spontaneously reassemble, and smoke never flows back into a cigarette. But what drives this constant increase in entropy? The emerging idea is that quantum entanglement is the engine. In the very early universe, just after the Big Bang, the cosmos was in a state of incredibly low entropy. It was a hot, dense, and remarkably simple soup where particles were not yet highly entangled. As the universe expanded and cooled, particles began to interact, collide, and spread apart. With every single one of these interactions, new quantum entanglements were forged. Think of it like a deck of cards. A new deck, perfectly ordered with all the suits in sequence, has very low entropy. When you shuffle that deck, you create randomness and disorder, increasing its entropy. But a shuffle also does something else. It creates correlations between the cards. The position of the Queen of Hearts is now linked to, or entangled with, the position of the Two of Clubs next to it. In the cosmic sense, as the universe evolves, it is constantly being shuffled. Every time two particles become entangled, the overall quantum state of the universe becomes more complex, more interconnected, and more correlated. This growing web of entanglement is what physicists call the increase of quantum complexity. It is this growth that directly corresponds to the increase in thermodynamic entropy, creating the irreversible gradient that we experience as the forward flow of time. Our ability to remember the past but not the future is not just a quirk of our brains. It is a direct consequence of the universe being in a state where entanglement has already happened. The past is the set of events that have already become correlated and recorded in this vast quantum network, while the future remains unentangled and undefined. So every new connection, every spooky link forged across space, is another tick of the cosmic clock, weaving the irreversible tapestry of time itself. The irreversible flow of time is a feature of our conscious experience, a steady stream of thoughts and sensations. But what if consciousness itself is a quantum phenomenon, born from the same spooky connections that stitch the cosmos together? This ninth theory plunges us into one of the most controversial ideas in modern science, the proposal that quantum entanglement is not just out in the stars, but is humming inside our very own brains, generating the light of awareness. The leading model for this radical concept is the orchestrated objective reduction theory, or ORCH, developed by physicist Roger Penrose and anesthesiologist Stuart Hameroff. They propose that the seat of consciousness is not simply the brain's neural network, but something far smaller, structures inside our neurons called microtubules. These tiny protein cylinders act as the brain's quantum computers. According to the theory, these microtubules can host quantum superpositions, where particles exist in multiple states at once, and these states can become entangled across vast networks of brain cells. It is the collapse of these widespread quantum superpositions, a process guided by the fundamental geometry of spacetime, that gives rise to a single, unified moment of conscious experience. Each flicker of awareness, each thought, is a quantum computation reaching its conclusion. This provides a potential answer to the binding problem, the puzzle of how the brain combines the input from millions of separate neurons into one seamless reality. Quantum entanglement could be the glue, instantly linking processes in different parts of the brain into a single, coherent whole. Yet, this theory faces immense skepticism. The brain is warm, wet, and chaotic, a seemingly disastrous environment for maintaining delicate quantum states, which typically require extreme cold and isolation to avoid a process called decoherence, where the quantum magic simply falls apart. Critics argue that any quantum superposition in the brain would be destroyed far too quickly to have any meaningful effect. However, the field of quantum biology is beginning to challenge these assumptions. We now know that quantum effects are essential in nature, from the way plants use quantum coherence in photosynthesis to the quantum compass that may guide migratory birds. The search is on for similar evidence within the brain. Could our most intimate sense of self, our consciousness, be the ultimate expression of the quantum world, a symphony of entangled particles playing out inside our heads? The same quantum connections that might power our consciousness could also hunt the universe's greatest phantom. Dark matter, the invisible substance that makes up roughly 85% of all the mass in the cosmos, has eluded every direct attempt to find it. Its presence is known only by its ghostly gravitational pull on galaxies, but its true nature remains one of physics' most profound mysteries. The 10th theory suggests we can turn the tables, using the most sensitive phenomenon we know, quantum entanglement, to finally detect this elusive shadow. The challenge is that dark matter particles, if they exist, interact with normal matter incredibly weakly, passing through our most sophisticated detectors like ghosts through a wall. But an entangled system is a state of perfect, delicate balance, a house of cards poised on a needle's point. The idea is that a passing dark matter particle, through even the faintest conceivable interaction, could be enough to topple that house. It would cause a subtle disruption in the entangled state, a measurable change known as decoherence, where the special quantum connection is lost. This disruption would be a clear signal, a tiny bell ringing in the quantum silence to announce a visitor. Scientists are designing incredibly precise experiments to listen for that bell. One approach uses networks of entangled atomic clocks, the most accurate timekeeping devices ever built. These clocks are synchronized through their quantum links, creating a stable, universal tick. A passing stream of certain types of dark matter could theoretically cause slight, correlated wobbles in the timing of these separated clocks, a synchronized glitch that would be the fingerprint of the invisible particle. Another method employs entangled magnetometers, devices that measure magnetic fields with astonishing sensitivity. These sensors are linked so that a magnetic signal in one is instantly reflected in its partner, allowing them to cancel out all the background noise of the cosmos. A dark matter particle with even a minuscule magnetic property would disturb this perfect cancellation, creating a blip that stands out against the quiet. By scaling up these experiments, creating vast, global networks of entangled sensors, we could cast a quantum net fine enough to catch the universe's most elusive prey. This would not just confirm dark matter's existence, it would finally tell us what it is, revealing the properties of the hidden architecture that holds our reality together. The same delicate threads that might reveal dark matter could also be unraveling the very nature of reality itself. Quantum entanglement does not just connect distant points in our universe, it might be the fragile bridge to an infinite number of others. This 11th theory plunges us into the many worlds interpretation of quantum mechanics, a breathtaking vision of a limitless multiverse. Every time a quantum particle exists in a superposition, simultaneously spinning both clockwise and counterclockwise, the universe does not simply pick one state at random. Instead, it splits. One entire universe branches off where the particle spins clockwise, and another, completely separate reality branches off where it spins counterclockwise. This happens with every single quantum event, every particle interaction, every possible choice, creating a constantly expanding tree of parallel existences where every possibility is played out. In one branch, you turned left on your way to work, while in another, you turned right. In one, the dinosaurs never went extinct, and in another, humanity never evolved at all. The number of these parallel worlds is truly infinite, yet a profound question remains: are these countless realities truly isolated, forever cut off from one another? Some physicists speculate they are not. They propose that when a universe splits in two, the newborn branches do not separate cleanly. A faint, residual quantum entanglement might linger between them, like a shared memory or an invisible umbilical cord connecting the diverging timelines. This weak entanglement would be a ghostly echo of their shared origin. While we could not simply walk into another universe, this connection could, in principle, leave faint, observable signatures. One tantalizing possibility involves delicate interference patterns. Just as two ripples on a pond can meet and create a new pattern of peaks and troughs, these entangled parallel realities might subtly influence each other, creating tiny, statistical anomalies in quantum experiments. We might see outcomes that are ever so slightly more or less likely than standard physics predicts, a whisper of interference from a neighboring world. This leads to an idea that borders on science fiction, the concept of inter-universal communication. If two branches of the multiverse remain entangled, could we ever learn to send a signal across the divide? It would not be a message written in radio waves, but something far more subtle, a coordinated manipulation of quantum probabilities. By carefully preparing a vast number of entangled particles in our universe and observing the patterns in their collapses, we might one day detect a corresponding, non-random pattern in a parallel world, a cosmic knock on the wall between realities. The message would not carry words, but it would carry meaning, the profound meaning that we are not alone in the vastness of all that is. We would know that our universe is just one leaf on an infinite, whispering tree. The same quantum magic that might weave the cosmos could be at work in the leaves of a tree. Here on Earth, scientists have uncovered something astonishing within the process of photosynthesis. When a plant absorbs sunlight, the energy from that photon needs to travel to a reaction center to be converted into chemical fuel. For decades, we assumed this was a random walk, a haphazard journey where the energy bounced between molecules until it stumbled upon its destination. But experiments reveal it is far more elegant. The energy travels as a quantum wave, exploring multiple pathways through the plant's cellular structure at once. It is guided by quantum coherence, a fragile state where molecules are linked in a coordinated dance, and this coherence is thought to be sustained by a delicate web of quantum entanglement among the energy-carrying particles. This allows the plant to find the most efficient route with near-perfect accuracy, a biological exploit of the quantum world that outperforms any human-designed solar cell. Now, let your mind journey to an exoplanet orbiting a dim red dwarf star. Sunlight there would be faint and precious. Any plant life that evolved in such an environment would face an immense pressure to harvest every possible photon. It is conceivable that these alien organisms would not just use quantum effects, they would have mastered them. Their entire biological machinery could be built upon a more robust and complex lattice of quantum entanglement, turning their world into a breathtakingly efficient light-capturing landscape. This leads to a revolutionary idea for the search for life. If such hyper-efficient quantum biology exists, it would leave a distinct chemical signature in the atmosphere of its planet. We might detect an atmospheric composition that is inexplicably rich in oxygen or complex hydrocarbons, a fingerprint of a biosphere operating at a level of energy efficiency that defies any known geological or non-quantum biological process. Our next great discovery of life beyond Earth may not come from a radio signal, but from reading the subtle quantum signature written in the light of a distant world's air. The universe is expanding at an accelerating rate, a fact that points to a mysterious force known as dark energy. Yet this discovery leads to one of the most embarrassing failures in all of theoretical physics. When we calculate how much energy should be boiling in the vacuum of empty space, the result is a number so catastrophically large it should have torn the cosmos apart in its first instant. The predicted energy is 10 to the power of 120 times greater than the tiny amount we actually observe. This is not a small error. It is the largest discrepancy between theory and experiment in the entire history of science. How can the universe be so stable when our best math says it should not exist at all? This is the cosmological constant problem, and the answer may lie in the silent web of entanglement that fills the cosmos. The theory suggests that the vacuum is not a collection of independent, energetic particles. Instead, it is a single, unified quantum system, a vast network where every flickering virtual particle is subtly linked to countless others through entanglement. This universal connectivity could act as a cosmic stabilizer. The immense positive energy generated by one part of the vacuum could be perfectly screened or cancelled out by the negative correlations inherent in its entangled partners elsewhere. Think of it like a frenetic, energetic crowd. If every person is shouting and moving independently, the total noise and chaos is overwhelming. But if the entire crowd is perfectly linked like a synchronized dance troupe, the chaotic movements of one individual are instantly countered by the coordinated, opposite movements of others. The result is not chaos, but a beautiful, stable pattern. The seemingly empty vacuum may be in a state of constant, violent activity, but its deep entanglement renders that activity perfectly balanced on the largest scales. We only perceive the tiny leftover, the minuscule net effect that was not quite cancelled, and this residual is the dark energy that gently pushes the universe apart. This provides a breathtakingly elegant solution, suggesting that the universe is not fine-tuned by accident. Its stability is an emergent property, a direct consequence of its profound quantum interconnectedness. The force shaping the cosmic destiny of galaxies is not a mysterious entity, but the quiet, collective harmony of a universe in perfect quantum conversation with itself. The silent hum of quantum connections might be tracing the very shape of the cosmos. A 14th theory proposes that we can use the patterns of entanglement as a cosmic cartography tool, drawing the map of spacetime itself by listening to its quantum whispers. This hinges on a profound discovery known as entanglement entropy. When you take a region of space like a box and look at the quantum fields inside it, they are entangled with the fields outside. The measure of this entanglement, its entropy, is not proportional to the volume of the box as you might intuitively think. Instead, it is directly proportional to the surface area of the box's boundary. This area law is a fundamental clue, suggesting that the information about what happens inside any volume of space is not stored throughout its interior, but is somehow encoded on its outer surface. It is as if you could learn everything about a room not by walking through it, but simply by reading the patterns etched on its walls. Physicists are now developing this idea into a powerful probe. By theoretically studying the entanglement patterns between different regions of the universe, they can work backwards to deduce the geometry that must connect them. If two areas of space are highly entangled, the spacetime between them must be smooth and continuous, like a gently rolling plane. But a sudden drop in entanglement, a cold spot in the quantum network, could indicate a severe warp in spacetime's fabric, a place where the geometry is strained or even torn. This method could allow us to detect the presence of cosmic phantoms that have eluded direct observation. A wormhole, for instance, would create a bizarre entanglement signature, linking two distant regions of space with a connection that is far stronger and more direct than standard geometry would allow. It would be like finding a secret tunnel on a map because two separate cities show an impossibly synchronized pattern of life. Similarly, cosmic strings, hypothetical defects in spacetime left over from the Big Bang that are thinner than an atom but incredibly dense, would leave a linear scar of disrupted entanglement across the sky. By analyzing the universe's quantum ledger, we could potentially see the ghostly contours of these exotic features imprinted upon it. We are learning to read the universe not by the light it emits, but by the silent, spooky links that define its true form. Our reality may be woven from tiny, indivisible threads. The 15th theory takes us to the absolute frontier, where we confront the ultimate goal of modern physics, a complete theory of quantum gravity. For a century, Einstein's general relativity and quantum mechanics have described our universe in brilliant but conflicting terms. One paints a smooth, continuous canvas of spacetime warped by mass and energy. The other reveals a granular, probabilistic world of frenetic particles. Unifying them is the great challenge, and the key may lie in how the fundamental bits of reality are intertwined. One leading approach is loop quantum gravity. This theory proposes that space itself is not a seamless continuum. Instead, it is woven from a fabric of unimaginably tiny, discrete loops, often called the atoms of space. These one-dimensional threads woven into networks create the three-dimensional reality we perceive, much like individual stitches in a sweater create a continuous garment. The properties of these spacetime atoms, their size and their spin, are quantized, meaning they can only exist in specific, discrete values. Now, here is where entanglement completes the picture. In this framework, these atoms of space are not isolated. They are profoundly interconnected in a vast, evolving network of quantum links. The entanglement between neighboring spacetime quanta defines their geometry, dictating how close or far they are from one another in the emerging fabric of space. Gravity, in this breathtaking view, is not a fundamental force. It is a statistical effect, an emergent phenomenon that arises from the collective behavior of this entangled network. Think of a still pond on a windless day. The surface appears perfectly smooth and flat, but if you could zoom in to the molecular level, you would see a chaotic dance of water molecules constantly jostling and interacting. The calm, continuous surface is an illusion that emerges from countless tiny, discrete events. In the same way, the smooth, warped geometry of spacetime described by Einstein is the large-scale illusion. The underlying truth is a seething network of entangled spacetime atoms. When a massive object like a star sits within this network, it disturbs the pattern of entanglement in its vicinity, changing the quantum connections between the spacetime atoms. This altered connectivity then manifests as the curvature of space, which we feel as the force of gravity. The planet orbiting a star is not being pulled by a mysterious force. It is simply following the path of least resistance through a cosmic landscape whose very weave has been reshaped by entanglement. We are finally seeing gravity for what it may truly be, a ghost in the machine, a story told by the silent, spooky conversations between the threads of reality itself. That ultimate question of origin leads us to a breathtakingly simple yet profound possibility. Our entire cosmos, with its hundreds of billions of galaxies, may be the result of a single, random quantum hiccup. This 16th theory proposes the universe was born from a spontaneous quantum fluctuation. In the strange realm of quantum mechanics, empty space is never truly empty. It is a vibrant sea of potential, where pairs of virtual particles and antiparticles constantly flicker into existence, borrowing energy from the vacuum for an immeasurably brief moment before annihilating each other and vanishing. Now imagine this process on the grandest conceivable scale. A fluctuation so vast it did not produce a mere particle pair, but an entire universe. In this picture, our cosmos is the ultimate free lunch, popping into being from a state of nothingness, or perhaps from a timeless, spaceless meta-universe we can never observe. But a universe born this way would not be a chaotic blob. The same quantum rules that governed its birth would have immediately woven structure into its fabric. The initial fluctuation would have created not one, but a vast number of entangled particle and field pairs, their fates irrevocably linked from the very first instant. These primordial entanglements are the cosmic seeds. As the universe inflated at a staggering rate, these tiny quantum correlations were stretched to astronomical sizes. The subtle differences in density and temperature they created became the gravitational wells where matter would eventually pool. Every galaxy cluster, every swirling nebula, every solitary star is the grown-up version of a microscopic quantum connection forged in the first fleeting moment of time. We are living in the amplified echo of that initial spooky link. This idea expands into an even more staggering vision. If our universe can bubble up from the quantum foam, then it is not alone. We could be part of a greater multiverse, an endless froth of cosmic bubbles, each with its own unique physics, each born from its own random quantum event. Our universe is not special, it is simply one that had the right conditions for us to exist and ask the question. Every characteristic we take for granted, the strength of gravity, the mass of an electron, could be the result of a random quantum draw in a cosmic lottery with infinite tickets. The deepest patterns of our reality were not designed, they were dealt from a shuffled deck at the dawn of everything. The silent quantum conversations weaving the cosmos could soon give us new eyes to see. A 17th theory takes entanglement from the abstract to the intensely practical, proposing a revolutionary form of detection known as quantum radar. Imagine trying to spot a perfectly black ship hidden in the pitch black of a moonless night. Conventional radar sends out a radio wave pulse and listens for its faint echo, but if the target is designed to absorb those waves or the background is filled with noise, the echo simply vanishes. Quantum radar changes the game entirely by using the spooky link between entangled photons. The system generates pairs of entangled light particles. One photon, the probe, is sent out into the void to scan for a target. Its entangled twin, the idler, is kept safe and isolated back at the source. This is the genius of the setup. The probe photon travels through space, and if it strikes something, a tiny fraction of its signal might bounce back, drowned out by a sea of random light and thermal noise. To any normal sensor, this returning signal would be indistinguishable from meaningless static, but the quantum radar is not normal. It possesses a secret key, the idler photon held in reserve. Because the two photons are entangled, their quantum states remain intimately connected no matter how far apart they travel. The system takes the incredibly weak returning signal and compares it directly with its pristine, untouched twin. Even if the probe photon is battered and degraded, its fundamental quantum relationship with the idler remains. By performing a specific type of measurement that checks for this surviving correlation, the radar can identify the faintest trace of a true signal against the chaotic background. It is like trying to hear a whisper in a roaring hurricane. A conventional microphone would pick up only the storm, but if you had the original whisperer standing next to you for comparison, your brain could somehow lock onto the familiar pattern. The radar does this with photons, filtering out the chaos to reveal the hidden object. The applications are profound. The most advanced stealth technology, designed to evade detection by absorbing or deflecting radar waves, would be rendered useless. An entangled photon probe interacting with a stealth craft's hull would still retain its quantum signature, betraying the vessel's presence. This could extend to finding small, dark asteroids that currently drift unseen through our solar system, posing a potential threat. The very phenomenon that connects the universe could become our ultimate sentinel, peering through the void with a sensitivity that seems to defy reality itself. The grand cosmic web we see today, a sprawling tapestry of galaxies and immense voids, might be the ghost of a quantum past. This 18th theory suggests that entanglement is a cosmic fossil record, the preserved blueprint from which all large-scale structure emerged. To understand this, we must journey back to the universe's first fleeting moments. Space was then a hot, dense, and remarkably uniform sea, but it was not perfectly smooth. Thanks to the uncertainty principle, tiny quantum fluctuations were constantly rippling through this primordial soup. Crucially, these fluctuations were not isolated events. Regions of slightly higher density here were quantum entangled with regions of slightly lower density over there. They were born connected, their fates intertwined in a spooky embrace across the infant cosmos. Then came the trigger of cosmic inflation, a period of unimaginably rapid expansion. In a fraction of a second, the universe ballooned in size, stretching every quantum fluctuation along with it. Those microscopic density differences and the entanglement links between them were blown up to truly astronomical proportions. What was once a quantum whisper became a gravitational shout. After inflation, gravity took over. The slightly denser regions, now grown to vast scales, had a stronger gravitational pull. They acted as seeds, drawing in more and more matter from their surroundings. Over billions of years, these seeds grew into the first stars, then galaxies, and eventually the immense clusters and superclusters we map today. The empty voids between them are the descendants of those initial low-density regions. The entire cosmic web, with its intricate filaments and gaping chasms, is not a random arrangement. Its specific pattern, the precise placement of every galaxy cluster, was dictated by the original map of quantum entanglement. We are literally looking at a fossil, an imprint of those first spooky connections stretched across the heavens. The universe has not forgotten its quantum origins. It has simply written them in the language of stars and galaxies, a permanent record of the invisible threads that once bound everything as one. The bizarre efficiency of quantum entanglement might be more than just a cosmic curiosity. It could be the very signature of a programmed reality. This 19th theory re-examines the simulation hypothesis, the idea that our universe is an artificial construct, a sophisticated digital rendering. For such a simulation to be possible, it would need to run on a computer of unimaginable power, yet even that power would have limits. Rendering every single particle and calculating every individual interaction across billions of galaxies in real time would be a computational nightmare, a task of infinite complexity. This is where quantum entanglement provides a shockingly elegant solution. Think of a video game designer creating a vast open world. Instead of programming every single blade of grass to move independently in the wind, which would melt the computer, the designer uses a trick. They create a rule that links the grass together so that when one patch sways, a correlated patch nearby sways in a predetermined way. This saves immense processing power. Quantum entanglement appears to be the universe's version of this optimization hack. The spooky connection between particles means the simulation does not need to calculate and update the state of each particle separately across vast distances. When two particles are entangled, their fates are linked by a single line of code. A change to one automatically and instantly updates the other without any calculation of a signal traveling through space. This non-local correlation is a massive shortcut, a way to maintain consistency across the cosmos without overloading the central processing unit. The apparent weirdness of entanglement, the fact that it seems to violate our intuitive sense of locality and time, could simply be an artifact of this optimized programming. We are seeing the underlying code of the simulation, a system where distance is an illusion rendered for our benefit, while the backend operates on a more efficient non-local network. The universe does not feel like a simulation because the graphics are so good. It feels real because the physics engine uses quantum entanglement as its most brilliant piece of compression software. We have been using entangled particles as sensors and probes, but what if they could become our messengers? The 20th theory explores quantum teleportation as a method for interstellar communication, a way to send the very essence of an object across the galaxy without ever moving it through space. This is not the teleportation of science fiction, where a person is disassembled and reassembled elsewhere. Instead, it is the teleportation of information, the flawless transmission of a quantum state from one location to another. The process begins with a pair of particles, like two photons, created together in a deeply entangled state. One of these particles, let us call it the traveler, is placed aboard a slow, conventional spacecraft and sent on a decades or centuries-long journey to a distant star. Its entangled twin, the homebody, remains securely with us on Earth. For all that time, the connection between them remains dormant, a silent thread spanning the light years. Now, suppose we want to send the complete quantum blueprint of an incredibly complex object, perhaps the design for a self-assembling probe or even the genetic code for a simple organism. We take this target object and we carefully bring it into contact with our homebody particle. We perform a special joint measurement that entangles the object with the homebody. This measurement does something remarkable. It destroys the original quantum state of the object on Earth, but in that very instant, because of the spooky link, the distant traveler particle at the star system is instantly projected into a new state that is intimately related to the original. However, this new state is not yet a perfect copy. The information from the joint measurement on Earth must now be sent to the distant star using a classical channel, like a radio signal. This radio transmission is limited by the speed of light, so it will take years to arrive. But here is the key. When that data packet finally reaches the distant spacecraft, the engineers there can use it to perform a specific operation on their traveler particle. They tweak it, applying the final instruction set, and in that moment the traveler particle is transformed. It becomes an exact replica of the original object's quantum state. We have not sent any matter, only information, yet we have recreated the most precise description of the object imaginable at a location light years away. This would allow a distant outpost to receive the complete schematics for a sophisticated machine, which a local 3D printer could then build with atomic precision. It is the ultimate data delivery system, using the slow speed of light for the instructions, but the spooky, instantaneous link of entanglement to lock in the perfect, uncopyable quantum signature. The colossal clouds of gas where stars are born seem governed by gravity alone, a slow and inevitable crush of matter. Yet hidden within that chaos, a subtle quantum hand may be guiding the collapse. Gravity pulls the vast molecular cloud together, but it is the initial microscopic distribution of density that decides where the first protostars will ignite. This is where quantum mechanics enters the stage. The particles within these clouds, from hydrogen molecules to specks of dust, are not isolated. They are subject to the same quantum rules that govern everything, and as they interact and collide in the frigid darkness, they can become quantum entangled. Their motions become correlated in a delicate, non-local dance. This network of entanglement could act as a hidden scaffold, organizing the cloud's internal structure. It might create preferred pathways for the collapse, channels where the gravitational fall of material becomes more efficient. Think of a crowd of people trying to exit a vast, dark field through a single small gate. If everyone moves randomly, the process is slow and chaotic. But if invisible threads connected small groups, coordinating their movement so they flow together in streams, the entire crowd would reach the exit far more quickly and smoothly. The quantum connections between particles may serve as those threads, subtly herding the gas into the densest pockets where gravity can then take over completely. This could explain the surprising efficiency with which these diffuse clouds transform into dense, blazing stars. Furthermore, the initial spin of a newborn star, a rotation inherited from the swirling cloud, might also bear a quantum signature. The entangled states of particles could influence the transfer of angular momentum, setting the star spinning on a specific axis and at a particular rate from its very first moments. This initial spin is not just a minor detail. It dictates the strength of the star's magnetic field and fundamentally shapes the protoplanetary disk of dust and gas that encircles it. The arrangement of planets, the location of asteroid belts, even the potential for life in that system, could all trace their lineage back to the quantum correlations that existed in the primordial cloud. The universe does not build its grandest structures with gravity alone. It uses the invisible threads of entanglement to weave order from the chaos, guiding gas and dust into the cradles of suns and worlds. Magnetic fields thread through the cosmos on an unimaginable scale, weaving between galaxies and stretching across vast intergalactic voids. Their origin is a profound puzzle, as these immense structures seem to defy a straightforward explanation. The 22nd theory suggests these magnetic ghosts are cosmic fossils, born from the quantum fizz of the universe's first moments. In the extreme heat and density following the Big Bang, the universe was filled with a soup of fundamental quantum fields. These fields were not static, they were wildly fluctuating and deeply entangled with one another. As the cosmos expanded and cooled, it underwent dramatic phase transitions, much like steam condensing into water. During these sudden shifts in the state of reality, the entangled quantum fields did not settle down uniformly. Their intricate connections created swirling imbalances and tiny currents in the primordial plasma. Think of a pot of water coming to a rolling boil. The bubbles form in a chaotic, seething dance, but if you could somehow freeze the entire pot in an instant, you would capture a snapshot of that frantic energy in the arrangement of the bubbles. In the early universe, the act of cooling and transitioning locked in the imprints of the quantum field's entangled dance. These imprints were minuscule magnetic seeds, weak patterns of polarity woven into the fabric of space itself. For billions of years, these seeds lay dormant. Then, as the first galaxies formed and began to spin, their colossal masses of ionized gas or plasma started to churn like a dynamo. This spinning plasma acted as a natural amplifier, stretching and twisting those weak primordial fields, winding them up into the powerful, organized magnetic structures we now detect spanning entire galaxies. The force that guides a compass needle on Earth and shapes the evolution of distant nebulae may not be a local phenomenon at all, but the amplified whisper of a quantum conversation that happened when time was young. The fundamental constants of our universe appear perfectly tuned for our existence, but one of them might be the most overlooked. The 23rd theory asks if quantum entanglement itself is a universal constant, a fixed number woven into the laws of physics that dictates the maximum strength and prevalence of these spooky connections. Just as the speed of light sets an absolute limit for motion and Planck's constant defines the granularity of the quantum world, an entanglement constant would determine the very capacity for correlation between particles. This limit might have been locked in during the universe's first moments, a fundamental parameter set at the birth of reality that governs how deeply any two quantum systems can become intertwined. It is the universe's built-in limit for togetherness, a cap on cosmic connectivity. The implications of such a constant are staggering to consider. What if its value were different in another universe, or had it been slightly weaker in our own? A universe with a lower entanglement constant would be a pale, disconnected place. The spooky links between particles would be more fragile, dissolving more easily and forming less readily. This weakness would ripple upward, affecting everything. Without robust entanglement to weave the fabric of space-time, gravity as we know it might be far weaker or not emerge at all. The cosmic web of galaxies might never have formed from those initial quantum seeds, leaving behind a diffuse, dark, and structureless cosmos. Chemistry and atomic bonds, which rely on quantum principles, could be profoundly altered, potentially preventing the formation of complex molecules necessary for life. Such a universe would be a silent, lonely expanse, devoid of the intricate structures that define our own. Conversely, a universe with a stronger entanglement constant would be almost unimaginably different. Particles would be bound in a tighter, more pervasive web of connection. Reality might be far more rigid and deterministic, with less room for the randomness and probability that gives our universe its richness and freedom. The very concepts of locality and separate objects might break down entirely in a cosmos where everything is instantly and powerfully linked to everything else. Our universe exists in a seemingly perfect Goldilocks zone for entanglement, strong enough to build stars and galaxies and life, yet weak enough to allow for individuality and chance. This raises a profound possibility. The constants we measure, from the strength of gravity to the mass of an electron, may not be independent. They could all be secondary consequences, emergent properties flowing from a more fundamental set of rules, with the entanglement constant sitting at the very core, quietly dictating the nature of reality itself. This same principle that links particles across a room could one day weave a web across the galaxy. The 24th theory envisions a galactic internet built not on radio towers, but on a process called entanglement swapping. This remarkable procedure allows two particles that have never met and have never interacted to become spookily connected. It works by introducing a third party. Imagine you have two separate pairs of entangled particles. Pair A consists of particles 1 and 2, which are entangled. Pair B consists of particles 3 and 4, which are also entangled but completely independent from the first pair. Now you bring particle 2 and particle 3 together at a central location and perform a special kind of joint measurement on them. This measurement forces them to become entangled with each other. In that very instant, a miraculous shift occurs. The act of entangling 2 and 3 automatically transfers the connection. Particles 1 and 4, which started out completely unrelated and may be on opposite sides of a city or a planet, suddenly become perfectly entangled with each other. A new, instantaneous link is born across a distance the original particles never traversed. This is the key to building a quantum network on a cosmic scale. Individual links of entangled particles are fragile and can only be maintained over limited distances before the connection is lost to decoherence. But with entanglement swapping, you can forge a chain. Picture a future where our first interstellar probes are not just explorers but communication nodes. A spacecraft travels to a star system 10 light-years away, carrying 1/2 of an entangled pair. Back on Earth, we hold its twin. We then send another probe 20 light-years out, also carrying 1/2 of a new entangled pair. When the second probe arrives, it performs entanglement, swapping with the first probe, linking its particle with the one back on Earth. Suddenly, we have a direct quantum connection spanning 30 light-years, even though no single particle traveled that entire distance. By placing a series of these quantum repeater stations throughout the galaxy, we could build a backbone of spooky links. A message encoded in the quantum states of particles could be passed along this chain, not by traveling through space, but by a cascading wave of entanglement swaps. The information would appear instantaneously at its destination, leaping across thousands of light-years without a single moment of delay. For an interstellar civilization, this would be transformative. Conversations between worlds would be as seamless as a video call next door. Collaborative projects, from building Dyson spheres to mapping dark matter flows, could be coordinated in real time. This quantum internet would also be inherently secure, as any attempt to eavesdrop on the quantum states would disrupt the delicate entanglement, immediately revealing the intrusion. The silent, spooky threads of the quantum world could become the bustling, instantaneous highways of a connected galactic community. At the very edge of a black hole, time itself begins to fracture. General relativity gives us a stunning prediction that, from our perspective watching from a safe distance, time for an object falling toward the event horizon appears to slow down, stretching seconds into eons until it seems to freeze completely. A ghostly image forever etched on the point of no return. But what happens when we weave quantum entanglement into this extreme picture? Consider a pair of entangled particles, two quantum twins sharing a single existence. One of them, let us call it the Explorer, is sent on a fatal journey into a black hole, while its sibling, the Witness, remains safely outside with us. As the Explorer approaches the event horizon, its time from our outside view grinds to a near halt, and because the two particles are spookily linked, this extreme time dilation does not just affect the doomed particle, it imprints itself upon the very nature of their quantum connection. The entangled state connecting them is now straddling two vastly different timelines. For the Witness particle outside, the quantum information describing its falling twin is not received all at once. It arrives stretched and distorted, as if the entire history of the Explorer's final moments is being played back in impossibly slow motion through their shared quantum link. It would be like watching a movie of someone's life, but the film reel is being fed through the projector, one single, agonizing frame per year. Each tiny change in the state of the infalling particle, each final interaction with the searing Hawking radiation at the horizon, registers as a gradual, drawn-out shift in its partner far away. This creates a bizarre quantum recording, a slow-motion replay of information encoded in the living state of the Witness particle. For physicists, this effect is more than a curiosity. it is a potential window into the heart of the unknown. By carefully monitoring the witness particle and tracking the excruciatingly slow evolution of its quantum state, we might be able to infer what is happening in those final moments before the horizon. We could gather data about the physics of the firewall, the nature of the singularity, or the process of information scrambling, all from the safety of the outside universe. It is a form of quantum archaeology, studying the most extreme environment in the cosmos by reading the subtle, time-dilated echoes it leaves on a particle it can never touch. This strange interplay between entanglement and time offers our first real glimpse into a theory of quantum gravity, showing us that the flow of time itself may be a deeply emergent property, born from the countless quantum connections that bind the universe together. This ceaseless quantum activity is not just empty noise. The vacuum of space is a vibrant ocean of entangled pairs, virtual particles, and their anti-particle twins, constantly flickering into existence for the briefest of moments before vanishing again. Each pair is born together in a spooky embrace, their fates linked from the very instant they borrow energy from the void. This endless, frantic dance of creation and annihilation is not without consequence. It fills the vacuum with a baseline energy, a hum of potential that permeates every cubic centimeter of the cosmos. We can even witness a direct effect of this phenomenon in a laboratory. Take two perfectly smooth, uncharged metal plates and place them incredibly close together in a vacuum. Outside the plates, the full spectrum of virtual particles can flicker into being, but in the narrow gap between them, only particles with specific wavelengths can appear. This creates a pressure imbalance, with more virtual particles pushing on the outside of the plates than on the inside. The plates are gently pushed together by the sheer force of this quantum activity. This is the Casimir effect, a measurable force generated by the ghostly pressure of the vacuum's entangled particles. Now, scale this idea up to the entire universe. If every point in space is seething with these entangled virtual pairs, the total vacuum energy should be immense. When physicists calculate this number, they arrive at a value so colossal it should have caused the universe to expand at a rate that tears atoms apart, rendering our existence impossible. Yet when we measure the actual expansion driven by dark energy, the value is almost zero, a number 120 orders of magnitude smaller. This is the cosmological constant problem, the most severe discrepancy between theory and observation in all of science. The solution may lie not in the energy of each individual virtual pair, but in the intricate web of entanglement that connects them all. The vacuum is not a collection of independent energy producers. It is a single, unified quantum system where every flickering pair is subtly linked to countless others. The immense positive energy generated in one location could be perfectly cancelled out by negative correlations from its entangled partners elsewhere in the cosmos. The vacuum's true nature is not one of chaotic, explosive power, but of perfect dynamic balance. The dark energy we observe, the gentle push accelerating the universe's expansion, might simply be the tiny leftover, the minuscule fraction of vacuum energy that was not quite cancelled by this cosmic entanglement. The fate of the entire universe could be dictated by the silent, harmonious conversation happening in the void. The faintest whispers of the cosmos are rippling through space right now, warping the very fabric of reality as they pass. These are gravitational waves predicted by Einstein and first detected by LIGO, which uses lasers traveling down immense tunnels to sense the microscopic stretching of spacetime. But a new vision for listening to the universe proposes a far more sensitive ear, one built not with lasers alone, but with the spooky handshake of entangled particles. Imagine replacing the laser beams in those 4-kilometer-long arms with a stream of entangled atoms or photons. In a conventional detector, a passing gravitational wave minutely changes the length of one arm relative to the other, and scientists measure the resulting shift in the laser light's interference pattern. But there is a fundamental limit to this precision, a blurriness imposed by the quantum nature of light itself. This is the standard quantum limit. An entangled system smashes through this barrier. Because the particles are linked, their quantum uncertainties are correlated, not independent. This allows the system to measure the relative change in the path lengths with a sensitivity that defies classical physics. It is like trying to hear a pin drop in a noisy room. LIGO is an exceptional listener, but an entangled detector would be like having a friend who can perfectly cancel out all the background noise for you, leaving only the pristine sound of the pin. The passing wave would disturb the delicate quantum state of the entangled particles in one arm slightly differently than in the other, and this discrepancy would be instantly revealed through their connection. A quantum gravitational wave observatory could detect frequencies far lower than LIGO can currently perceive. This would open a portal to cosmic events of unimaginable scale. We could listen to the stately, slow-motion dance of supermassive black holes, millions of times heavier than our Sun, as they spiral together in the hearts of distant galaxies. We might even hear the faintest echo of all, the remnant gravitational rumble from the universe's birth in the Big Bang, a direct signal from the moment of creation itself. By harnessing entanglement, we are not just building a better detector, we are learning to read the subtle quantum tremors written upon spacetime by the most violent and profound events in existence. That strange power we have to influence a particle's past is not confined to the laboratory. The quantum eraser experiment reveals a truth so bizarre it seems to rewrite the rules of time itself. In the classic setup, a particle like a photon is sent towards a screen through a pair of slits. If you do not measure which slit it goes through, it behaves like a wave, creating an interference pattern. But if you set up a detector to see its path, it acts like a single particle and the pattern vanishes. The true strangeness comes with the delayed choice quantum eraser. Here, you can let the photon pass through the slits, and only after it has already hit the final screen, you choose whether to look at the path information. Astonishingly, that later choice seems to determine whether the photon behaved as a wave or a particle in the past. It is as if your decision today reaches back and edits what happened yesterday. Now, stretch this concept across the cosmos. Theorists propose a version of this experiment using light from the most distant objects we can see, quasars whose light has traveled for billions of years to reach us. This light can be gravitationally lensed, meaning its path is bent by a massive galaxy between us and the quasar, creating multiple images of the same quasar in our sky. We can treat these two light paths as the two slits in a cosmic double-slit experiment. The light from each path has been traveling for eons, its journey seemingly complete. But we hold the final piece of the puzzle. We can choose to measure the arriving photons in a way that erases the information about which path they took. If we do this, we should see a telltale interference pattern, proving the light behaved as a wave for its entire multi-billion-year journey. Yet if we choose to measure which path each photon came from, that pattern disappears, indicating it traveled as a particle. Our choice, made here and now, would appear to reach back across time to influence the behavior of that light when it began its journey, long before our planet even existed. This is not magic, it is a consequence of the universe being a deeply interconnected quantum system where past and future are not as separate as they seem. The cosmic quantum eraser pushes the boundary of causality to its absolute limit, suggesting that in an entangled universe, the present may not just remember the past, it may actively participate in its creation. The hierarchy problem cuts to the very heart of why our universe feels so familiar. It asks a deceptively simple question: why is gravity so unimaginably weaker than all the other forces? The strength of the electromagnetic force, for instance, is a trillion times more powerful than gravity. This is not just a minor curiosity. It points to a deep instability in our understanding of mass. The Higgs boson, the particle that gives other particles their mass, should naturally be driven to an energy scale quadrillions of times heavier than it actually is, due to its quantum interactions with other particles, especially the heavy top quark. This would make atoms impossible and life unthinkable. Our reality seems to require an impossibly precise and seemingly random cancellation of these enormous quantum effects to leave us with the lightweight particles we see. The solution might not be a random fine-tuning, but a geometric one woven from quantum entanglement. Certain theories propose that our universe is a three-dimensional membrane or brain floating within a higher dimensional space. In the Randall-Sundrum model, gravity is naturally weak because it is diluted, spreading out into a warped extra dimension that is inaccessible to us. But what anchors our familiar particles to our own brain, preventing them from simply drifting off into the bulk of higher dimensional space? This is where the spooky connection enters the picture. The theory suggests that every particle we can detect, like the Higgs boson or the top quark, is not a solitary entity. It is one half of an entangled pair. Its quantum twin, its spooky partner, exists not in our dimension but in another brain, separated from us by a hidden dimension. This entanglement across the dimensional divide creates a powerful binding effect. It pins the particle to our brain, but it also does something more profound. The immense quantum fluctuations that would normally drive the particle's mass to an astronomically high value are now shared with its invisible partner. The two particles act as a single quantum system, and their shared energy is distributed across the dimensional gap. The result is a natural suppression, a cancellation that emerges from the geometry of reality itself. The mass we measure in our world is not the full story. It is the residual, the leftover after this cosmic balancing act between entangled twins. The reason gravity feels so weak and particles have the masses they do is not an accident. It is the direct consequence of our universe being intimately linked through a web of quantum entanglement to a hidden reality just beyond our perception. The fabric of our world is stabilized by invisible threads reaching into other dimensions. The universe is heading for a profound and chilling silence. After all the stars have burned out and all the black holes have evaporated, the cosmos will approach its final state, known as the heat death. Here, everything reaches a uniform, frigid temperature, and entropy, the measure of disorder, hits its maximum. The universe becomes a vast, dark, and dilute sea of particles, a cosmic graveyard where no energy can flow and no new structures can form. It is the end of time in any meaningful sense. Yet, even in this absolute stillness, a question remains. What happens to the spooky threads of quantum entanglement that once wove the cosmos together? One possibility is that they slowly, inexorably decay. Over timescales so immense they dwarf the current age of the universe, the last fragile entanglements would succumb to decoherence, their delicate connections severed by the relentless, if faint, background hum of the remaining particles. The universe would not only be dark and cold, but also completely disconnected, every particle an island, utterly alone in the void. But another, far more beautiful theory offers a different vision. As the cosmos expands and cools towards absolute zero, all the remaining particles could lose their individual identities and settle into the lowest possible energy state. They would merge into a single, unified quantum field, a cosmic Bose-Einstein condensate on a universal scale. In this final state, the entire universe would achieve a perfect global entanglement. Every particle would be spookily linked to every other particle, a frozen, silent network of pure correlation. This would be the last vestige of structure, the final whisper of information left in the cosmos. It would be a connection without communication, a memory of a universe that was preserved forever in a single, shared quantum state. The heat death would not be a blank nothingness, but a cosmos that has finally achieved perfect static unity. The same phenomenon that sparked the birth of galaxies and powered the arrow of time would become its final, eternal monument. From the silent hum of a galactic internet to the very threads weaving our reality, we have journeyed through 30 incredible visions. Each theory, in its own way, seizes upon the same bizarre property of quantum entanglement to probe the deepest mysteries of existence. It connects distant particles, stabilizes the vacuum of space, and might even generate the flow of time and the light of consciousness. This strange phenomenon is far more than a laboratory curiosity. It appears to be a fundamental feature of the cosmos, a silent architect working behind the curtain of everything we see and are. So we leave you with this question to ponder. Which of these entangled theories do you find the most compelling, and what do you think it reveals about the true nature of our universe? Share your thoughts in the comments below and subscribe for more deep dives into the greatest space mysteries.